Alright, hello students! Alright, so this is the first video lecture for your class in these really strange times. Okay, so what we're going to do today is we're going to do Lab 7. So I would like all of you to have your lab manuals in front of you as we do this, and I would like you to turn to page 58 of your lab manual. Okay, so you will get to, it should say Atmospheric Humidity at the top here. Alright, so I would also like to, before we start, let you know that you need to read through this lab. I am going to step you through. I am going to help break down and explain a lot of what is in this lab, but you will need to read this before you do the actual hand-in assignment. Okay. So let's get to the first section, and it is atmospheric moisture. And I'm going to go through this like I said quickly. Atmospheric moisture refers to water vapor and precipitation, oh my god, I got there, in the Earth's atmosphere. The amount of water vapor in the atmosphere is called humidity. Okay, so when we talk about temperature and humidity, you need to know that temperature and relative humidity are inversely related. As temperature increases, relative humidity decreases. Okay, that is like probably the first, like if you're taking notes or trying to follow along in here, you need to know. It says it in the second paragraph here of your lab manual. It will tell you that temperature and relative humidity are inversely related. The amount of water vapor a parcel of air can hold increases with temperature. Therefore, as the temperature of an air parcel increases, the relative humidity decreases. All right. The next paragraph will talk about dew point, and put simply, dew point is the temperature at which air becomes saturated. Okay. Also, we will get into talking about the albedo of a surface, and what that means is the reflectivity, the amount of light that is reflected off of that surface. The lighter the surface, the more light that is reflected. The darker the surface, the more that is absorbed. You find this when we look at the moon. The moon is a very light object. As a celestial body goes, it is extremely reflective, and we see that every night. The moonlight is just the sunlight being reflected off the moon back at us. All right. Okay, so the part of this lab that kind of sucks that you guys didn't get to do is this would have been an outdoor lab. We were going to use a scientific instrument to go take measurements of the temperature and the humidity using something called a Sling Psychrometer. Okay, so this is a neat, if not a little bit old, piece of technology. And it is two pieces, and as you can see here, there are two mercury thermometers. And what we would do is we would, this part here is called the wick, and we would wet down the wick, and then we would mount this portion of the psychrometer here. Okay, now here's where we're going to find out the sling part. So you take it, and you sling it, just like this. Okay. Yeah, so you guys would have gone outside to 4 different locations and done this. Because of these strange circumstances, I have done it for you. So, yeah, okay, this is oddly mesmerizing. I'm going to put this down. Okay. Alright, so on page 59 of your lab manual, you will talk about the Sling Psychrometer. And it says, it is a tool designed to allow you to determine dew point temperature and relative humidity. Okay, so something else to note here in the second paragraph, it says the amount of cooling, the wet bulb, which is the wick that you would have wet down, this is the wet bulb and the dry bulb, the amount of cooling that takes place is directly proportional to the amount of water in the air. So what you would do here when you sling the psychrometer, right, you would go outside, you would take this instrument, and after wetting down the wick, you would swing it for a minute, and then you would take the temperature that is on the thermometers, and you would see the difference between the two. Okay, and you would mark that down. So in the practice here on page 59. The practice on page 59, you see that the first one is done for you, but the second one says that they took a dry bulb temperature of 58 degrees Fahrenheit and a wet bulb temperature of 56 degrees Fahrenheit, which gives you the wet bulb depression, which is the difference between the two, the difference between the 68 and the 56, gives you 12 degrees Fahrenheit. Okay, so what do you do with that? We have the relative humidity that you need to find. You are going to go to the next 2 pages. And the next 2 pages are 2 charts. Something to take note. One of these charts is in Celsius, the chart on page 60. And one of these charts is in Fahrenheit for the temperature. Be sure that you use the corresponding chart. So right now it is asking you to find it in Fahrenheit. So what you would do is you would go to the dry bulb in Fahrenheit. So you would go to this, the y-axis here, and you would find the 68, I believe. Yes, you would find the 68. But then you would see the depression of the wet bulb thermometer, and you would find that there's a 12-degree difference, and you would go downward and find that the relative humidity is 46%. So the temperature is your y-axis, okay? The temperature is your y-axis, and the depression is your x-axis, and you want to be sure that you find the corresponding number between the two. All right. And again, be very mindful whether you are taking readings in Fahrenheit or Celsius. Okay. So I would like you to go to, we're going to jump ahead here, and we're going to go to page 64. Page 64. All right. So page 64 brings us a different concept here. We're kind of still staying within the wet and dry areas of the air, but we're going to talk about adiabatic lapse rates. I can tell you this will most likely be a test question about what does the term adiabatic refer to, and it refers to moving air. Those are the 2 words that if I say adiabatic, you say moving air. It's kind of like when I teach my other geology or physical geography classes, metamorphic means heat and pressure. This means moving air. So, all right. So there are 2 things to know about the adiabatic lapse rate. So when we discuss this, we are generally talking about tracking the change in temperature through altitude as we increase or decrease through the atmosphere. I'm sure those of you who have Dr. Cicchetti, he does some really great work on this. I think the way he describes it is fantastic, but I am going to try and explain it to you as a lab manual would like you to. So we're going to talk about the wet adiabatic lapse rate and the dry adiabatic lapse rate. So the whiler and the dowler. Okay, so the wet adiabatic lapse rate. From here on out, you will see WALR, wet adiabatic lapse rate. And then you will get the dry. Dry adiabatic lapse rate, DALR, the dowler. The whiler and the dowler. Okay. All right. So you will see a graphic on your lab manual here on page 64. And what it will show you is that when you have an area without saturated atmosphere, the temperature changes in a different way than it would should the air be saturated. So if the air is wet, saturated, has a lot of moisture in it, the lapse rate will be, and 5 degrees Celsius, 5 degrees Celsius every 1,000 meters. Okay. But if the air is dry, on these graphics you will see that they denote dry as no clouds. I would also like to note that condensation begins at the dew point, not always where clouds begin, but for the purposes of this lab, we are going to work with where the clouds begin is where the wet lapse rate starts. But the dry is 10 degrees every 1,000 meters. Okay. So you will see here, there's a practice on page 64 where they would like you to find the temperature of a parcel of air as it changes between 300 meters to 800 meters in altitude and the air is not saturated. Okay, and this is how much will the temperature drop? What is the difference in temperature if the air is saturated? Okay, so what I would like you to do is, if you are following along with your lab manual, please do the practice. Please do the practice using this information right here. The wet adiabatic lapse rate being 5 degrees C every 1,000 meters, and the dry being 10 degrees C every 1,000 meters. All right. Okay. So, for the lab, for what you are going to turn in for me, normally we would have done, like I said, I would have sent you outside with the Sling Psychrometer, and I would have had you take readings. Well, lucky for you, I have done this for you. So the charts here behind me, I am going to fill out these charts, and you will have to use this information in the lab to finish it. All right, so here's what I'm going to do. I have noted 4 different locations from which I took readings. I have the parking lot, the Martin Hall lawn, the breezeway, which is between Martin Hall and McGee, and the classroom, or this room. This isn't our classroom, this is a different place. Okay, what I'm going to do is I'm going to fill out these with different temperatures. Took 3 readings, so we have, and this is going to be in Fahrenheit. So we have 60 degrees Fahrenheit and 76 dry, 59 and 74 and 62 and 77. Okay. All right. So that is for the parking lot. I'm really hoping you guys can see these things clearly. After I'm done writing these in, I'm going to give you a chance to look at these. I will step away for a minute. All right, so the Martin Hall lawn. All right, 68. Okay, 59. 69 degrees F. 69 again. Okay. All right. So that is the readings that I took for the Martin Hall lawn. Okay, now we're going to continue to the breezeway. So. All right. Okay, and for the last was the classroom. And you'll probably notice a little bit of difference here. Okay, and one more. Okay, so what I'm going to do is I'm going to take a step away here just for a second. If you would like to pause the video to write these down in your lab manual, feel free to do so. Let me just step away for a second here. Okay. So, the last thing I would like to go over on page 66 is your lab. And what you're going to do is you are going to use these numbers, these readings for this lab. Row F, the RH, it's going to say RH percentage meter reading. You do not have to do the RH. Please do not do that. Only do A through E for each one of these. A through E. Okay. There are some questions on page 67 that you will have to answer. Do keep in mind things about albedo and the differences and how the relations between dew point and humidity interact. And on page 68, you will have a picture of a mountain, and the picture of this mountain will be giving you different elevations, and you will have to tell me at what temperature the air is at, given whether it is a dry rate, or a wet rate. And keep in mind that for the purposes of this exercise, the clouds denote a wet adiabatic lapse rate. Okay. All right. So you will turn that into me. Please, when you send me pictures of these, please put your name on each page. I know that seems excessive, but it makes it easier for me in case I have to download these off of the email or whatever submission area I'm having this be in. It is just easier for me, and I do not want to mix anyone up. So please put your name at the top of each page, each and every one. Additionally, if you need help, if you have any questions, you can email me. I am keeping a very close eye on my email. That's the GeoHistorian at gmail.com. And if you have a question that you believe can be answered quickly through a text, feel free. I will be posting both of my contact informations in the Canvas post with which this video will be attached to. So, two things about that. One, don't call me, please. I'm not going to pick up. I don't pick up strange numbers. Two, when you message me, please tell me your name and what class you are in. That will help me out a lot. And as long as it is an answer that I can give you within maybe a few short sentences, I'm not going to write, a whole book about it. But the option is there. I am here to help in any way you need. So, that said, I think that's everything. Good luck. I will let this sit here one last time. But thank you and best of luck. And if you need anything, feel free to let me know.